开始哦。我以为如果是的话，那我不确定。
So our second speaker is Professor Naoto Shiraishi. And Naoto graduated from the University of Tokyo. And at the moment he is at University Kakushin. University. This pronunciation is not so good. Yeah, and in 2018, he got the prize, Young Scientist Award of the Physical Society. And this award is very prestigious. So before him, in 2016 is Suzuka Ito, right?
Yeah.
Suzuka Ito. And 2011 is Takahiro Sagawa. So he is the successor of these people. But, okay, these two people are at the moment in the University of Tokyo. So, but before they arrived at the University of Tokyo, they all attended the workshop or winter school in Taiwan. So it seems that attending the winter school will promote and increase the possibility to arrive at Tokyo University. So today I create a new possibility for you, investor possibility, and invite him to come here. Okay, then let's welcome our speaker.
Thank you for a kind and explanation. I hope this prediction is true. Okay, I'm Naoto Shiraishi. I came from Gakushuin University. Today I talk about some introductory part of stochastic thermodynamics. Some of the part is overlap with Jason's previous talk, but my talk considers the system with discrete states in contrast to the Jason system, which is a continuous space. So this is, I think, the main difference, but some part they have some overlaps. Okay. In conventional thermodynamics, we consider macroscopic systems, and the observables takes a certain determinate value. There is no fluctuation. However, in stochastic thermodynamics, we want to consider small systems with thermal fluctuation. So the observable does not have a single value, but there exists much thermal fluctuation. An example is for the particles and molecular motors. As we explained, we consider the system with discrete finite number of states. For example, in this protein, in this case, the protein has 6 stable states. If we want to consider the system with continuous space, we consider the proper discretization and take a continuous limit. So this explanation covers all types of systems, including continuous systems. But we mainly take a very simple example with very few states. We consider system with attached to a heat bath or several heat baths. And we only observe this system. So this heat bath induce the stochastic nature of time of evolution of a system. Let's take an example. We consider protein which has 3 stable states. One is a closed state, and middle state, and open state. Then, for example, the previous state is a middle, and then now it closed. So, for example, this protein is still in the closed state with probability 4/5, but it go back to the middle state with probability 1/5. For example, this type of process is a stochastic process. If this probability doesn't depend on the previous state here, so whether the previous state is middle or close, then this probability same, then we call this process as a Markov process. In this talk, we consider Markov process. In the terminology of stochastic process, the state of system is a probability distribution on the microscopic states. So for example, if the probability distribution is that the closed state appears with probability 0.3, and the middle appears with probability 0.5, and the open appears with 0.2, then this probability distribution is one state of the system. And we describe it as the probability vector. So for example, P1, P2, P3 represent the probability of the 1 closed, 2 middle, and 3 open. So in this case, the state can be written as the vector 0.3, 0.1, 0.2. Now, we consider the case that the state, before we consider the situation that the time is discrete, but now we want to consider the continuous time case. We consider that at time t, the state is middle with probability 1. So the state is always middle state. Then after a very short time delta t, then for example, the state goes to the closed state with probability 0.1 delta t. And this state goes to the open state with 0.2 delta t. Then of course the state is still in the middle state with probability 1 minus 0.3 delta t. Then the probability vector at time t plus delta t can be written as this. Then by considering these two difference, then dividing by delta t, then the derivative of this probability distribution can be obtained as this, in this case. Now, then we generalize this observation as this. So, in general, the time evolution of a Markov process can be written as this. Here, this is the probability vector, and this is the transition matrix. In the case of the previous slide, R12, which is the probability that the present state is 2. And then after the short time delta t, then the state is 1. This is given by this matrix element. So R12 is 0.1. So this, because this is 0.1 delta t. In a similar manner, R32 is 0.2 because this probability is 0.2 delta t, and R22 here, this is minus 0.3 because this is the probability and the state escape from middle state is 0.3, and we add the minus sign. In general, the transition matrix R, this matrix R, should satisfy these two conditions. First one is non-negativity. The off-diagonal element of this matrix should be non-negative because transition probability must be non-negative. The second condition is normalization condition. This claims that the summation over the vertical direction should be 0 for any column, because the summation of the probability distribution should be always 1. This normalization condition guarantees this condition. Before here, we explain the mathematical framework of stochastic thermodynamics. So, for example, this framework is applicable to non-physical systems. That is, For example, the biological evolution system and some other, for example, economical systems, and maybe more abstract situation. But we want to consider thermodynamic system. So we now put physics into this framework. What is the situation we want to consider? We consider situation that the system is attached to heat bath. So for simplicity, we mainly consider the case of a single heat bath for simplicity. But our explanation is easily generalized to a general case with several heat baths. Our situation is typical situation is that there exists some protein or some molecular motors in isothermal condition. This is a typical situation. Now, we require some from physical observation. First, we assign the energy of each state. Then we can consider the equilibrium state or canonical distribution. The canonical distribution of this system is given by this. This is a well-known elementary part, which is run in undergraduate student. Then, because a system is attached to a heat bath, and heat bath induces the system relax to the equilibrium state with this temperature. So, if beta is the same as the inverse temperature of the heat bath, then this probability distribution should be invariant, does not evolve. So, the time evolution of the time derivative of this distribution, so this means that the multiplying the transition rate to this Gibbs distribution should be zero vector. So this is a requirement from the equilibrium condition. So we say that this is also invariant condition. So PG Gibbs distribution does not change. This is a requirement. Because the heat bath should induce the thermal relaxation, this condition should be satisfied in any physical system. Moreover, but not only the invariant condition, but also some more stronger condition is satisfied in many physical systems. This is the detailed balance condition. Detailed balance condition claims that if the system is in equilibrium, then there are no probability current exists between any two microscopic states. So, for example, there is 3 states, so there is 6 possible transitions. Then we consider this. We focus on these 2 states. Then there is no probability current between these 2 states. This is the requirement of detailed balance condition. I'm sorry, I forgot to say that we consider the system is in Gibbs distribution. In Gibbs distribution, there is no probability current. This is the requirement of detailed balance condition. So we summarize the invariant condition and detailed balance condition. We can compare these to the picture. If we require only the invariant condition, there may have a finite probability current. In this case, there exists probability current this direction. But the stationary distribution should be Gibbs. But there exists some current. This type of situation occurs if there exists some parity odd variables, such as the momentum or the system is under magnetic field. But if such a parameter doesn't exist, then the system usually satisfies the detailed balance condition. So these two probability current is balanced, and there is no net probability current between these 2 states. And any pair of 2 states satisfy this condition. This is the detailed balance condition. Now we define some physical quantities. as Jason explained, we also introduce energy, heat, and work. First, the internal energy is easily defined because internal energy is equal to average of energy. But this is defined as this. This is very intuitive definition. We next define as heat. Because the complex system system and heat bath is isolated. So if the state change, then the energy difference should be absorbed by heat bath. So for example, if the state 1 changes to state 2, then the energy difference E1 minus E2 should be emitted by to heat bath. So we can define the heat by the energy difference times probability current from J to I. And we take all the pair of I and J. And using normalization condition, we can transform this expression as this. This is the definition of heat. We finally define the work. To consider this, we treat different system from the protein with 3 stable states. Because in the case of protein, there is no work, no external agent. We consider the well with a step, and we label the state 1 if the particle is in the bottom, and if we call this state as state 2 if the particle is on the step. Then and the probability distribution is denoted by P1 and P2. Then we consider the raising of the step. The energy difference is labeled as delta E2. Then the expectation value of the energy of the system is changing. And this energy change comes from externally because the change of this step induces this change. So the process requires average energy P2 delta E2. So this amount of energy should be regarded as work. In general, the work is defined as energy change due to the energy change of state energy. So the definition of work, this is the work rate, is given as this. This is the speed of the change in each of energy in each state times the probability that the system takes this state I. Using this definition, we recover the first law of thermodynamics. So the energy change, the change in both internal energy is the sum of the work and heat. This is easily derived as this. Now we move to another most important quantity in thermodynamics, entropy. Because the complex system of the principal system and heat bath is isolated, so the entropy, the sum of the entropy of heat bath and the system should increase. This is the law of entropy increase. In other words, the delta S system and plus delta S bath is non-negative. In conventional thermodynamics, entropy is defined for equilibrium state. This entropy satisfies this relation in a quasi-static process. Entropy of heat bath can be well defined by this fact. Because the heat bath is always in equilibrium, we can define temperature. So by using this relation, the entropy change in heat bath can be given by this relation. We know how to define the heat, so we can define the entropy of heat bath. But how to define the entropy of system? System is highly non-equilibrium. So the conventional thermodynamics does not tell this answer. So we employ information theory. We use entropy in information theory. Let's take an example of the weather in Taipei as an example. If the weather is sunny, this is a very usual event. So the Taiwanese people do not surprised with this weather. However, if it snows in Taipei, then this is a very rare event. So the Taiwanese people are very surprised at this event. We want to quantify the degree of surprise, or it's called also surpriser. We give some measure of surprise. There is some action of surpriser. First, the surpriser is non-negative and continuous function. And the important requirement is that if two events, A and B, are independent events, then the surpriser for the event that both A and B occurs is the summation of the surpriser for the A occurs and the surpriser for the event B occurs. Then the surpriser is uniquely determined by this function. Here Ln is the logarithm with the base of a Napier number. C is a positive constant, and we usually set C is 1. And P is the probability that the event occurs. So we can plot the surpriser as this. And the horizontal axis is the probability for each event. If an event always occurs, then of course this event induces no surprise at all. In contrast, if the event occurs very rare, then this event induces very big surprise. And we consider the average of surpriser as this. Then this quantity, average of surpriser, is equal to Shannon entropy. So the Shannon entropy quantifies the average of surpriser. If an event occurs very randomly, then the degree of surpriser is very large. Then so Shannon entropy is large. In contrast, if event occurs almost deterministically, then this situation induces very small surpriser. So Shannon entropy becomes very small. For example, let's consider the weather again. I think the 1% snowy day is very overestimated, but I'll use this example. Okay, and in this case, the surpriser can be calculated as this. And we take that the surpriser times its probability. So for example, the 0.250 is 0.357 times 0.7. Although the snowy day have a very big surpriser, because this probability is very small, the contribution to Shannon entropy is very small, 0.046. This is very small compared to these two. And then for this weather case, the Shannon entropy is 0.655. If we consider another example, coin toss. And the P is the probability of the head of the coin. Then we can plot the horizontal axis with P and the vertical axis, the Shannon entropy divided by log 2. In this case, the maximum is 1. And if the coin is very fair, both the head and tail appear with probability half. In this case, the Shannon entropy is maximum. In contrast, if the coin is very biased, this coin always gives the tail. In this very unfair coin, the Shannon entropy is minimum 0. This is the property of Shannon entropy. And the important fact is that in equilibrium distribution, Gibbs distribution, Shannon entropy reproduce the equilibrium Boltzmann entropy. For example, if the system is a microcanonical ensemble, in this case, due to the equipartition, the probability for each state gives by the 1 over the number of states, omega. Then calculating the Shannon entropy, Shannon entropy is log omega. This is consistent with the Boltzmann formula. Here we set the Boltzmann constant to 1. Another example is the canonical ensemble. In this case, probability for each state is given by this canonical distribution. Then Shannon entropy can be calculated as this, and this is the beta times the expectation energy minus expectation. The Helmholtz-Free energy. This is entropy. So in these cases, in equilibrium distribution, Shannon entropy coincides with equilibrium statistical entropy. So Shannon entropy can be regarded as a kind of generalization of equilibrium entropy. And in fact, if we define entropy by using Shannon entropy, for the case that the system is attached to a heat bath, then this definition indeed works. This definition reproduces the second law. So we define entropy of fluctuating small systems by Shannon entropy. So information entropy always appears in stochastic thermodynamics. Some people consider that the information appeared only in the, for example, problems of Maxwell's demon, but this is not the case. All information entropy always appears. Then we go back to my problem. In this system, we define entropy of the heat bath by using this relation. And entropy of the system can be given by the difference of Shannon entropy. So we can define the entropy increase of the total system as this. We usually denote this quantity by sigma. This is called entropy production. Now we consider entropy production rate, which is the entropy production divided by time. So this quantity can be calculated as this. This is almost a definition, or almost inserting this definition. And this is calculated as this. Here we use a master equation, this relation. So we obtain this expression. But if the system satisfies the detailed balance condition, we have a more convenient and useful expression as this. This expression can be obtained because due to the detailed balance condition, we have this relation. And using normalization condition, we find that this relation, this is same as this, is equal to entropy production rate. This term is the entropy increase of the heat bath, and this term is the entropy, Shannon entropy change in the system. Now, we prove that this entropy production rate is non-negative, which is the second law of thermodynamics in stochastic thermodynamics. In conventional thermodynamics, the second law is the observation, action, empirical law. In contrast, we can derive the second law in stochastic thermodynamics. But we remark that this is not the derivation of the second law or conventional macroscopic system, because we've already used the knowledge of conventional thermodynamics in the definition of entropy production. So this is not the big derivation of the conventional thermodynamics. But in stochastic thermodynamics, if we assume the property of thermodynamics in heat bath, then the composite system of heat bath and the system should satisfy the second law. We can derive this. This is not action. We first consider as an easier case, the case with detail balance. In this case, we can easily prove the second law. We use this relation in the proof. This relation can be easily confirmed because this term, log A over B, is non-negative if and only if A minus B is non-negative. So if this term is positive, this term is positive. This term is negative, this term is negative. So this inequality is confirmed. Now, the interproduction rate is given as this, if the system satisfies the detail balance condition. But because I and j is a dummy index, we exchange I and j, so we find that this is equal to this relation. So this term is the same as this, takes the same form. So this is non-negative. We can easily prove this. Now we want to go to the next general case. But before going to the proof for the general case, we introduce a Kullback-Leibler divergence or relative entropy. Kullback-Leibler divergence quantifies the difference between two distributions, AI and BI, with the same sum. The Kullback-Leibler divergence is defined as this. This quantity is a kind of should distance between two distributions. If the two distributions close, then Kullback-Leibler divergence takes a small quantity, and if these two are highly different, then this takes a very large value. We can prove that the Kullback-Leibler divergence is non-negative. This is confirmed by this relation. X minus 1 is larger than log x. This is very elementary fact, and visually prove this. Not a proof, but it is visually confirmed. Then, Kullback-Leibler divergence can be written as this. We here exchange A and BI, and we put the minus sign. Then, applying this relation, we find this. Here, because there exists a minus sign, the direction of the this inequality is exchanged. So we find this. So this is equal to this relation. So because the two distributions have the same sum, this is 0. So the Kullback-Leibler divergence is non-negative. Okay, we go back to our program. To prove this, we introduce dual transition matrix. Dual transition matrix is defined as this in our case. We remember that dual transition matrix is indeed transition matrix. In other words, this transition matrix indeed satisfies the normalization condition because this summation with I is equal to this, but we know that the canonical distribution is invariant. So this term is 0. So we find that this summation, the R tilde with the summation I, is also 0. This is a normalization condition. So R tilde is indeed transition matrix. We use the invariance of canonical distribution. Now we introduce the general expression of end production rate, which is satisfied not only for the system with detail balance, but also general system. This is the expression of entropy production rate, and this is written as this because of the normalization condition. Now we can see that if I equals j, then this term is 0 and this term is 0. So we can remove the case of I equals j, and we take only the summation for I not equal j. Then this we transform this relation as this. Here we use the fact that the duality transition rate is given as this. This is almost a definition of the dual tension rate. By construction, this relation is satisfied by construction. Now, we find that this summation with I not equal j is equal to this relation because we take the sum only for I, so only the diagonal term remains. But the both diagonal term is equal between the dual tension rate and the original tension rate, because if this I equal j, then these two terms are the same. So diagonal terms are the same between dual and original. So this is same as the dual tension matrix, and then we find that this this sum is equal to this sum. So entropy production rate given as this can be regarded as a curvature divergence between this quantity, this distribution and distribution. Here, the subscript runs all a pair of I and j except I equal j. Then, because curvature divergence is non-negative, we find that entropy production rate is non-negative in any system. Okay, we summarize my tutorial talk. We construct a framework of stochastic thermodynamics, and we define heat, work, and internal energy, and entropy production. In particular, entropy production is non-negative for any systems. Thank you for listening.
Thank you. Question?
Maybe it's not very important, but you mentioned there's a physics. Oh, sorry. So as you mentioned, there was a condition called the invariant condition in the very beginning. I'd like to ask again what it means again.
Meaning?
Yes.
Physical meaning of the physical meaning is that the Gibbs distribution is invariant. This because if the physical situation is very simple. If there exists a very large heat bath with temperature T, and then we have a very small system, and it is no equilibrium attached to this heat bath, and then leave, and then we wait for a long time, then this small system should go to the equilibrium distribution, and then this state never change. This is the expected property, I think. So if the state is in equilibrium, then this system never change. So if the state is in equilibrium, this system never change. This is the physical meaning of invariant condition.
Thank you. I remember there was another place where you had a picture with only two of the states.
Detail balance.
Yeah, with the detail balance.
Okay, this one.
No, it was the one with the detail balance and an invariant condition in the same page. Right?
And no. This is understood as this. For example, this if only invariant condition is required, then there may have some current between these small microscopic states, but the distribution is Gibbs. This indeed occurs. For example, the system is under magnetic field. In this case, there is a Lorentzian force, and then this particle has a momentum. This is not a discrete, but in this case, there exists some current, microscopic current can exist. And detailed balance condition does not allow this type of situation. So the detailed balance condition is satisfied if there exists no such kind of magnetic field and momentum. But in many cases, detailed balance condition is also satisfied.
question? So here you show entropy production is positive for this.
Non-negative.
Non-negative for discrete system.
Yeah.
Is it also true for continuous?
Yes, because if we want to treat a continuous system, then we first consider the discretization of the space. So, for example, if we want to consider Brownian particle, then the state is very considered as a small lattice. Then the Brownian particle hop to the next site with some probability properly determined by the original Brownian motion. And then, of course, this is a state discrete. These results are satisfied. And then finally, we take the continuum limit. Then all the results are recovered for continuous system.
So the proof is straightforward.
Yeah, I think so. Yeah.
Straightforward. Other question? If not, let's thank the speaker again. Okay, we move on to the third speaker.